Hello, I'm Aditya Krishna, and I'll be presenting on computational approaches for DNA motif finding. This project explores how deep learning, especially CNNs, can advance detection of biologically meaningful sequence motifs. DNA motifs are short patterns crucial for gene regulation, yet their identification is difficult due to the sequence variability and noise. This project uses CNNs to improve the detection accuracy and efficiency of motifs. Our goal is to build a robust model, reduce the false positives, then benchmark against the known existing models like mean and debug. So here's an outline of the presentation. We'll cover the introduction, objectives, backgrounds, methodology, the model design, and my current status, and finally to the findings. So DNA motifs usually 6 to 20 base pairs long are key binding sites for transcription factors and play a central role in gene expression. Mutations in these motifs are often linked to diseases. Traditional methods like chips like are costly and condition specific and consume a lot of time. And computational techniques offer scalability but struggle with noise and variability. With AI, especially deep learning methods, we aim to automate the pattern recognition and enhance the prediction across different data sets and species. So our project has four main objectives. Develop a CNN model for motive detection, enhance existing algorithms by improving scalability and accuracy, reduce false positives through data augmentation and interpretability, then uh, benchmark against the known tools using the data sets from Meme and Code and Jasper. So traditional methods include probabilistic models like Meme and Gibbs sampling, then deterministic models like PWMs, that is the position weight matrices. While Meme is robust for small data sets, it struggles with large data sets. Then Gibbs sampling can identify the binding sites pretty accurately, but is really sensitive to the initialization part. So PWMs are simple, but they ignore the dependencies between the positions. Now we come to the modern approaches. Deep bind applies DNNs to one hot-coded DNA sequences, learning the motifs automatically, but require large label data sets. Hybrid models like DanQ combine the CNNs with LSTMs to learn both spatial and long-range patterns. Transformer-based models such as DNA BERT they go further by capturing the global interactions and offering pre-trained architectures for motive discovery. Then to the methodology, we start with raw DNA sequences from the databases like ENCODE and Jasper. One hot coding preserves the base order basically, while the KMR embeddings capture the local context. So, but in this project, this is the original methodology. But in this, so what I have done is I have created a synthetic data set. Uh, Rather than taking a data set from Jasper or Google steps just to try it out. So the only difference is that I created my own data set of the sequence games. That's a DNA sequence. That's all. Then this data augmentation is also done like we introduce minor mutations to the data, which increases the robustness. Okay. Then this is the model design. So our CNN model includes three convolutional layers with increasing filter depth to detect patterns across multiple motif lengths. Now, review activation function is added in order to introduce nonlinearity. Then pooling layers reduce the dimensionality of the sequences. Then the fully connected layers at the end finalize the classification with the then I have also applied dropout as in it is a measure to decrease the chance of overfitting the model. So then The model optimization. So the model is trained on 70% of the data, 15% the rest from the rest of 30%, 15% of it is for validation, and the next 15% of it is for testing. Then we have chosen hyperparameters, we have taken hyperparameters, learning rate, batches, and used early stopping as well. So the evaluation will be based on accuracy and AUC ROC score. Then finally, we'll compare it with mean and deep bind models. Then, so I'll show you my code. So this is the code for creating the uh, dummy data set. These are the nucleotides. So basically, we embed motive at random instances, uh, and it will create the DNS sequence, and it may contain some of the motifs like G, AT, 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 and R. Then it looks like this. Then the next is about data pre-processing. Basically, in this code, we are one-hot coding the vectors. You can see that suppose if the vector is A G so A will A is represented by 1000, G is represented by 0010, and C 0100, and T as 0001. So basically, all the gamers are one hot coded in here. Then this is our CNN model. This includes three, as I said, this includes three convolutional layers. Pooling is also applied here. Uh, then dropout is added. This is a forward propagation function. This is the model. So uh, I have trained it up to 20 epochs of the dataset, and the synthetic dataset contains 10,000 rows as well. So I just wanted to say that. So yeah, as it is a synthetic dataset, it automatically overfitted actually. So the training accuracy that I got was 99%, but the highest testing accuracy was about 55%. So If if I had used if I had used some other actual data set from Jasper or anything, it would have been better. It will be better, and it would have been better. The training. This is the plot accuracy across the box and stuff. So this orange line should have been here actually. If I used another actual data set. So this is the code for plotting the confusion matrix and the classification spot. This is the confusion matrix. It is not that good actually. The precision recall F1 score, it's not that good. As I said, this is a synthetic data set. Uh, so that's all. So the summary. Um, and so basically the things in summary, the CNN models significantly improve the motive discovery by learning the biologically relevant patterns and scaling efficiently. Then this model outperforms meme and or meme then basically uh, so in the future, looking ahead, we plan as I plan to extend this model to multi-species motor detection, prediction, and integrate that the attention mechanisms, basically introducing the concept of transformers for into this, and I'll be sharing this code to my GitHub. Thank you and have a nice day.